So as I said, we're going to start with simple, as in not very powerful models of computation. They won't be necessarily simple, but they're not as powerful models of computation. And so the simplest computations we're going to show are able to capture things like text processing. So looking for a file name to match a certain pattern, looking for a file whose name contains CSE105, for example, is something that we're going to be able to do with the simplest level of computation. Also, the first step in any compiler is a tokenizing step or a lexical analyzer step, where the compiler has to take the whole string of ASCII symbols that it's given and try to cut it up into pieces that say, hey, this is an identifier, this is a variable name, this is an instruction. And cutting it up into those pieces is what we can do using automata and using regular expressions. Okay? So these kinds of techniques are available to us with this very simple model of computation. Also, if you've taken 140, or if you've done anything with robots, you'll notice that the model of computation we have here that is at this lowest level of computation is very similar to the finite state machines you may have designed. Okay? So the idea with this very beginning is that we're giving ourselves a little bit of computational power. We've got a notion of states and we've got a notion of computation, but we're going to try to strip down to the bare bones the resources that are available to us and see what we can do at the very bare minimum. Okay? So that means that we're going to look for simple patterns. And so let's build up from those simplest patterns, what we consider to be simplest. Okay? So for example, if we don't want to match anything, if we don't want to say that any string has a particular property, if we want to have the property be represented by the empty set, then that's pretty simple. Right? We can just build a process that always says, no, 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 no. I'm not going to accept anything. Okay? So that's a fairly simple pattern. That should be captured even at this smallest model of computation. Bless you. Similarly, if we just have a couple of special cases, we can think of them as being encoded in a lookup table. If we just have a finite lookup table of examples, that should be fairly easy to check against computationally. So we can think of a lookup table as just listing out the elements that we want to say yes to, and then we say no to everything else. Okay? So that also should be captured in the simplest model of computation. And then going in the other direction, if we just want to say yes to everything and say, yeah, everything has the property that I care about, and basically match with everything in the universe, so all possible strings, then that's also a fairly simple thing to do. Right? It's a constant algorithm that always says yes, 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 right? Without worrying about the different properties that our strings might have other than that. So all of these seem like fairly simple collections of strings that we should be able to describe or discriminate in a simple model of computation. And so what we're going to do for the rest of today's class is talk about how to describe patterns that are simple. Okay? And so we're going to have an inductive definition of a family of languages, sets of strings, that are described by simple patterns. So we're going to build up these simple patterns based on some of these examples.